Okay, so I will say very briefly, this is the fourth event of 2021, which is held in this unusual fashion for the reason that we all know. The previous events were devoted to the COVID pandemic, and this is the first one that explores other areas of physics or science that are of interest to us. Just for our guests, we have colloquia of the whole class of sciences together, which comprises people in physics, mathematics, biology, and chemistry. And so this event is meant to be as an interdisciplinary nature. And so we ask you to take this into account. The next event will take place on May the 26th. It will be devoted to astrochemistry. Today the time is special. We usually meet at 3 p.m., but of course for reasons due to the time shift between here and Los Angeles, we meet at 6. I guess I can let Vittorio give a proper introduction to our speaker before we start. Thank you very much again for accepting our invitation. I will turn off my microphone and remove also the video to.
Okay, so thank you, Augusto, for the introduction. So today I'm very happy to introduce you Fernando Brandao. Fernando is one of the most influential researcher in the field of quantum information theory and quantum computing. He is currently the head of the quantum algorithm division of Amazon Web Services, and is a professor at the theoretical physics at Caltech. So he's very young. He got his PhD in 2008 from the Imperial College of London, then moved to where he also became a postdoctoral fellow. And then after a brief period that he spent as a postdoc at the University of Minas Gerais, Brazil, he became assistant professor in physics there, and he moved as a senior researcher at ETH. And after that, he became a reader in computer science at the University College of London. And at the same time, he was a researcher for Microsoft. Then finally, in 2018, he became a visiting faculty at Google's Quantum A lab. And after that, he became professor at Caltech. So it is important to also to remind you that last year in 2020, he was awarded by the American Physical Society with the prestigious award, the Landauer and Bennett Award in quantum computing. So essentially, the research field that is covered by Fernando includes different aspects of quantum computing and quantum information theory, but he has also worked in fields like quantum many-body theory, thermodynamics, and statistical mechanics. So in this special sector, he has contributed a lot by studying the relation between entanglement and other physical properties like correlation length, heat capacity, and so on and so forth. And this study has helped us to better understanding the notion of area laws, how area laws emerge in this system, the connection with the second principle of thermodynamics, and also how we could simulate thermalization process on this system. So I would like also to mention the fact that he's one of basically the researcher that started a new way of approaching thermodynamics by considering it as a sort of resource theory. Okay, so given that in the today talk, he will be focused on quantum computers. And in particularly, he's going to present us what means to build a quantum computer, and most importantly, what we can run on those machines. And so I think now I can leave the stage to Fernando, that is going to start with his presentation. In case you want to ask question, please simply raise your hand by pressing the button, and then I will give you the possibility of posing the question. So please, Fernando.
Thanks a lot, Augusto and Vittorio, for the introduction and for the invitation. Really happy to be here talking to you. I wish I was, like in Italy right now, giving this talk in right face to face, but it's not possible yet. So I'm very happy that at least we have, technology to allow us to do that. I wanna, yes, please feel free to interrupt me at any point and ask questions. As Vittorio said, what I want to talk to you today about is like a question that many people in the field, right, try to make progress there, and it's a very long-term goal, but it is the goal of eventually building quantum computers, and I want to address two aspects of it. The first is, how we are trying to build quantum computers and what are the challenges there. And the second is why we want to build a quantum computers, right? So why do you think if you can build it, there will be many interesting things we'll be able to run there? So let me go ahead. So what is quantum computing, right? So in one sentence, quantum computing explores the intricate physical laws of the microscopic world to perform computation in novel and improved ways. So we know, right, that if you go to the microscopic world and we try to understand, like electrons, photons, atoms, molecules, so on, then the physics that describes that is very different to the physics that we learn in school, right? Like Newton's law and so on. This physics described by quantum mechanics, and it turns out that the physics is so different that there is also new possibilities for processing information and for doing computation. And quantum computing is just trying to explore these unique features of quantum mechanics for novel forms of computation. So there is a lot of potential. There is a potential for a new paradigm in computing, and this is, has been known for a few decades now, or at least like that's the hope that is the case. But there is very hard scientific and engineering challenges to build quantum hardware at the scale that we would need to really, put this potential into work. And I'll mention some of them later on. So both like what is the best approach to build these quantum computers, and also what we can call the killer apps, right? What we want to run there and really get some advantage to science and to society and to industry of this new paradigm is still unclear, and a lot of work is still required there. But it's a good place to be at, right? Because there is, it's an exciting field and it's scientifically very stimulating. And on top of that, there is some potential technological applications. So before I go to quantum computers, right? So today, right, I think you read in the press a lot, right? And in grant proposals and so on about quantum technologies and, how we hope they will be important in this century. But actually, if you think about quantum technologies, like from last century, quantum mechanics has already been very useful, right, for new technology. So for example, the NMR machine, right? So we cannot make it work without understanding quantum mechanics, or the laser, or even a transistor, right? So we have to understand, quantum mechanics of solid state to really be able to come up with the transistor, which is the building block of our current computing systems today. So quantum mechanics definitely already had an impact, right, in the past. But I think it's fair to say that in the past, people had to understand quantum mechanics to devise this, to engineer these devices, but they tried to tame the quantum effects, right? So they want to understand and make this thing work, not really exploring fully these like unusual and weird aspects of quantum mechanics, but really trying to control them and mitigate them to get the useful technology to work. And what we want to do now is a little bit different. So now we want to go to the other side. So what is this, unusual aspects of quantum mechanics, right, that we want to explore? So let me just have a slide just mentioning them. I won't get into a lot of details, but it's useful to mention. So as I said, quantum mechanics, right, describes the physics of the very small, right, of atoms, photons, electrons, and so on. And the basic units of quantum mechanics and of quantum computing, right? So for the physicists, they have been calling this like a two-level system for a long time. Now, because of the analogy with classical bits, we call this a qubit as well. But that's just the simplest in the two-level system in quantum mechanics, right? So you have a physical system. You can think, for example, about an electron, and this electron can spin in two directions, right? Clockwise or anti-clockwise. And they correspond to distinct physical states, right? And if it's spinning clockwise, we can call this the zero states. I use this notation that's using quantum mechanics, right? This cat-bra notation, but if you don't know it, you can just think that that's a label for the states, clockwise, and there's another state anti-clockwise. So far nothing special. But then if you think about the physical description of this degree of freedom of the quantum system, in quantum mechanics, we have to consider a superposition or a linear combination of being in one state or the other with some amplitudes. And these amplitudes, alpha and beta, they are just complex numbers, but they have a relation to a probability distribution, and that's the following. If we take the absolute value and take the square and sum, it gives 1. So alpha square and beta square, they form a probability distribution. So in that sense, you can think, well, that's not very different, right, than if you just have a classical system on two states, 0 and 1, and we have some probability distribution over the states because of some lack of knowledge. And in a sense, it's true. But then quantum mechanics you can think as some version of probability theory, but where instead of using the probability distribution, we use these amplitudes instead. So if you make a measurement, if you observe the system, we get either 0 or 1, and we get 0 probability alpha square, we get 1 with probability beta square. But because we have these amplitudes instead of the probability on the fundamental level, there is many different things that happen. So you can have, the superposition of states, but then because it's superposition, you should think at similar to what happened with waves. So you can make them interfere, for example. So you have these interference effects that do not happen if you just have a probability distribution. If you have many quantum systems, as I mentioned in the next slides, you can have also this feature of entanglement. You can have like stronger kinds of correlations than what you can have with probability distributions. And then the idea, what we want to do on quantum computing is to try to explore these features. So going more specifically to computation, right? Why we might think that it's useful to use these quantum systems for computation. So let me show you a plot. So this is the use of the Department of Energy in the US supercomputer by area from 2018. So they give this every year. I should have used a more updated one, but it doesn't change much. But then you can see the areas, right? And the most used is like Earth environmental systems, okay? Then there is second chemistry, third material science, fourth fusion energy, fifth nuclear energy, sixth high energy physics. So you see that a very large fraction, right, of the use of this supercomputer is devoted to simulating quantum systems, right? So all that I indicated, it boils down to try to simulate large quantum systems. And why is it so costly to simulate these large quantum systems? Well, because it turns out that the cost grows exponentially with the system size, right? So if I have n qubits, for example, right, then this quantum state that I mentioned before for 1 qubit, now instead of having 2 complex numbers, you need 2 to the n complex numbers, right? Because for each one of all possible configurations of 0 and 1, you need this complex coefficient there. So it's like 2 to the n parameters and steps, right? If you just do it in the worst case, to simulate systems of n qubits. And that's exactly, because of this phenomenon of entanglement between qubits. So entanglement is what doesn't allow us to break this description into description of individual systems, as we can do with a probability distribution, right? We can always sample and have just a configuration. Quantum mechanically, we cannot really do that. And then very quickly, right? 2 to the n is very, very fast growth, right? So 30 qubits, take 16 gigabytes to store. 40 qubits take 16 terabytes, 50 qubits like 16 petabytes. That's kind of our limits of supercomputers, right, today. And then as few as 300, around 300 qubits, like 10 to the 100, right? It's completely out of reach. Of course, this doesn't mean, right, that physicists don't have very smart ways of simulating these quantum systems, that we cannot understand them, right? That's kind of what physics has done, right, in the last 100 years, and it works well. But there's definitely limits to what we can do, and I'll discuss a little bit more later these limits and how quantum might help there. But you see that there is, just simulating quantum systems, there is a kind of a fundamental hurdle here using our conventional computers. And this has been recognized actually a long time ago, but probably the first person to talk about this was Richard Feynman. He gave this very inspiring notes. It's called Simulating Physics with Computers in '81. So 40 years ago already. And he has this quote, I'll read for you. So he says, trying to find a computer simulation of physics seems to me to be an excellent program to follow out. Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So he had a lot of insight here, right? So it was very early on, but he knew that, right, really moving forward, it's important, right? So use computers to understand nature, right? It gives a lot of power to us. But then, of course, nature on the fundamental level is not classical. We have to use quantum mechanics to describe it. And then, if you actually want to make a simulation of nature, right, that is effective, you have to use, you have to make it quantum mechanical, right? And what he means make quantum mechanical, I think he was suggesting the idea of a quantum computer to really use a quantum mechanics or quantum physical systems to build a computer, and then use this computer to understand, physics better. And of course, as we know very well, it's a good problem. It's a wonderful problem, but it is not easy at all, right? And I'll tell you some of the challenges. But then, for many people, this was the first time that the idea of quantum computing was considered. Then after that, many other pioneers, right, start thinking about that. And the rest is history, and I'll mention some other breakthroughs soon. So what we hope will be the quantum technology of the century is, there's other ideas, but the one I focus here is the idea of quantum computing. And there we want to use very well-controlled quantum systems that we build in the lab for computation, right? So what is this on very concrete terms? So think about how our computers work, right? So of course, there's many levels of abstraction, right? And that's very important. But on the most basic level, it's all like a Boolean logic, right? It's a Boolean circuit. So imagine that, like in this example, you have 3 bits, A, B, and C. They can be either 0 or 1, each one of them. And then we just start applying, gates on 2 bits, right? You can have an AND gate, you can have an XOR gate, right? And so each one only touches two bits. It does an extremely simple operation. But if you combine them, we can make more interesting logic, right? For example, here in this simple circle, you can compute this Q function on the left-hand side. And if you just build more and more complicated circuits, we can do all the great stuff that we do in computing today, right? So there's like an art in building the circuits, but the building blocks are extremely simple and we can control very well. And very importantly, right, today with transistors, we can make these gates very, very, very precise, right? So there is an error in these gates 1 every 10 to the 12 times, or 10 to the 13 times even. Basically, yeah, our computers, when this happens, very unlikely we can just reset the computer and that's it, right? But it's very important, the reliability as well, and we will go back to that. So what is the idea? Well, we want to do the same thing for quantum physics now, right? So we have the same thing as our bits, but it's our qubits that I mentioned before. And now we want to make some physical operations, but quantum mechanical physical operations on them that acts only on 1 qubit. For example, this is what we call a Hadamard Gates. It just maps like 0 to a superposition of 0 and 1, and maps 1 into a superposition of 0 minus 1 with a different phase. And we also want to couple these qubits, right? So this is, you can think in the lab, it's like a 2-qubit operation that you implement where you couple these 2 qubits. In that case, this is what we call a control Z operation. So condition on the state of the first qubit, if it's 0 or 1, it puts a phase on the state of the second qubit, puts a factor of -1 in front of the states. And this can generate correlations between them. And then here, you can just think about a circuit. And what the circuit does is to prepare this quantum state, right? It's a very simple circuit, it does that. But if we have more complex circuits now, and if noise is low, right, that's very important as well, we might be able to do more interesting quantum algorithms there, right? Okay, before I talk about what are the quantum algorithms, right, that we are studying today and that we think are worthwhile implementing, how is this actually done in the lab, right? So right now it's like you could say that there is a race on scaling up these quantum systems, right? And I don't think there is like a winner yet. It's very early on, and everyone has very serious challenge to scaling. But many people are trying on different approaches. And these are like 4 of the approaches, I think, that I want to mention to you. So one of them is called superconducting qubits. And that's an approach that we are doing at Amazon. So we've been working a lot on this and some variants of it that I'll mention a little bit later. But the idea here is that you go to cryogenic temperatures, very low temperatures, like 10, 20 millikelvin. And you build like a LC circuit as we learned in school, right? Like with inductors, capacitors, and so on. But we make everything superconducting. And then if it at these very low temperatures, it becomes quantum mechanical, the description. And then, for example, you can have quantized states for the currents in these LC circuits. That's fine, but that's like a linear system. It's not useful yet. But now you can put a non-linear system there, which is called Joseph junction. Joseph got a Nobel Prize for that a long time ago. And this is basically a non-linear electrical element there for this. And this is what allows us to implement the qubits. So now we have 2 levels that are called a qubits of this electric circuit, quantized electric circuit. And the third level is like detuned from that. There is a non-linearity there. And therefore, these first 2 levels is our qubits. And then we can control this qubit using microwave signals. So that's nice because we can use, microwave control system, which is out there, and they work pretty well. They're reliable. And it's solid states, right? Even though, we need to be superconducting, so that's kind of unusual. And we can try to scale up. So people have been able to scale up this. For example, the experiment done by Google recently up to like 50 qubits. And the error rates are like 0.5%. for a 2-qubit gate. So it's kind of good, but very far from where we want to be. And I'll touch these numbers again soon. But that's the state of the art. And it has been fast progress. Okay, like 10 years ago, the error rates were like abysmal. You cannot do a gate like they'll be close to 90% when it started, or like 95%. Just really bad. So there's been a lot of improvements, and we can hope that maybe there'll be more, but it remains to be seen. Another interesting approach is trapped ions. So this was the first, or maybe was the first way that people proposed to build a quantum computer. What you do is that you use, like a trap, which is a bunch of like E&M fields there, electromagnetic fields, and then you trap ions, right? So they are like charged particles, so they will repel each other. But then because of this trap, right, this E&M system that you put around them, you can trap them in a line. And then they're here in the line, but they can vibrate. So with lasers, you can manipulate some electronic states, and that's your qubits there. But then these lasers, you can also couple the motional degree of freedom. So they vibrate, right? And they vibrate, and when they vibrate, they couple to the other ones because they are positively charged. And in that way, you can implement the gates, right? By really tuning the lasers in the right way and implement the gates. People can trap like a few something like, okay, trap up to like 100, but trap and manipulate, they can do around like 20, 30, right, today. If you just have one ion, is really good gates, even better than superconducting qubits, maybe like 0.1%. But once you put them more in the trap, it becomes a little bit more challenging, and then it's like around 1%, something like this, the gates today. And that's true for everyone. We are about like a few, less than 1%, and we can go to 50, something like this for qubits in the best case. So it's still very early on. There is also another atomic approach, is Rydberg atoms. You excite the atoms to a very high level, and then they're very strongly coupled. And it's very nice. You can use optical tweezers, and then you can put them pretty much any shape you want. like a Paris, group in Paris did like this Eiffel Tower there, right? And then you can use lasers to manipulate them again. Is developing very fast. Is the newest approach. In terms of gates, the gates are still pretty noisy, more noisy than the other ones, but it's going fast. So it's very interesting to see the development there. And the last one, it's kind of nice. You do everything in photonics, right? And you can even do on silicon, which people doing foundries, the silicon chips, right? So you can use the same thing that you can use this infrastructure. The challenge here is that photons are very hard to interact with each other, right? So like the initial preparation of the right photonic state is very challenging, and we don't have much experimental progress for doing that, but many people are trying, right? So in all of these approaches, this is done in academia, right? So there is many lab groups doing that. But what is interesting is more recently, I guess, industry is also trying that, right? So like Google, IBM, now Amazon, right, and some startups like Rigetti and others, they try superconducting qubits. Honeywell and a startup IonQ is trying trapped ions, and also a startup from Austria, right, also trapped ions, which is it's called Alpine Quantum Computing, I think. Rubber Atoms, there is a startup trying QERA, and Silicon Photonics, there is PsiQuantum, a startup trying as well. So this is nice because it's a way to scale up the systems, right? It's pretty expensive to scale up the system. It's very hard as well. So it's good to have these investments. At the same time, it's not just a question of money. There is serious scientific questions to be sorted out there. So let's see, right, the development. So I think the next 5 to 10 years will be exciting to see what happens there. But why you want to build a quantum computer? So because we want to do something with it, right? So we have these applications for quantum computing. And I think it's fair to say that we just don't know yet, right? Like what are the right applications for quantum computer? Because we don't have one yet, right? So think about all the applications we have today of our computers, right? They all emerge. I mean, we knew a few of them before, right? At least potentially, but they all emerge once we have the computers, right? We can try them out. We can run a bunch of heuristics on them, right? And right now we are basically trying to develop quantum algorithms with a pen and a paper, right? So really we come up with a quantum circuit for something, and we try to prove that it works well, and then we have compare with the best classical algorithms, right? So this makes the work on quantum algorithms pretty challenging today. But it's still, even considering that, we have identified like a few applications where quantum can give a very big benefits, and I think this is a very good indication that if we figure out the technology, you'll be very worthwhile to have a quantum computer, right? But I think it's fair to say we don't have the killer applications yet, right? They remain to be discovered. So let me mention a few of them, the ones that we know today, and talk to you about the scale, right? How many qubits you need to do them. But let me mention the catch here, because this will be revised soon. The catch is that we are assuming perfect qubits with no noise, okay? And that's not how that's not reality, right? So we will have to address this soon. But let's consider this for now. So maybe the most famous application of quantum computing is in cryptography, and it's to break cryptography, right? Which is maybe not what we should do. But that got the interest of everyone. And in '94, Peter Shor, he was at HCHC back then. Now he's a professor at MIT. He found a quantum algorithm that could break RSA. Okay, and RSA is the public key crypto system that we use today. And it works pretty well, right? So whenever we buy online or we do anything online, we're using it. And the fact you cannot break it is based on the fact that it's very hard, as far as we know, to factor big numbers, right? So if I give you 15 is 5 times 3. That's easy enough. But if I give you a number with like 2048 digits, it's very, very costly to factor it. Okay? And the best methods that we have will take many centuries for doing so. And then they create this RSA crypto system exactly based on these facts. But now what Shor showed is that actually there is a very efficient quantum algorithm that runs in cubic time in the number of digits for breaking RSA. So in practical terms, if you want to break RSA where the key size is 2048, which is what you use today, with 6,000 qubits, you could break it, depending on the clock cycle, but in a time from minutes to hours. So very quickly. And this is because many governments start thinking about quantum computers and why again people start thinking cryptography as well, how they can come up with a cryptography, a public key cryptography which is safe against quantum computers as well, which is an interesting area of research today. So this is like is an application of quantum computer, I think, that shows the power, but that's hopefully we won't use, right? Because I don't think we should be building this technology to break other people's secrets. But I guess the application that Feynman had in mind, right, for quantum computing, and that many scientists are excited about, is that it would just be a great way to understand physics and chemistry, right, and material science better, right? So if we have the quantum computer, we can simulate like any quantum mechanical process we want in a much more efficient way, right? That we can do classically. We won't have this exponential scaling that we have classically, right? When we try to simulate quantum mechanical systems, we just have like a, in the best case, is a polynomial scaling, can be even linear scaling, right? So because we're using qubits. So many people work on that. There's a lot to talk about, but for example, in physics and chemistry, right? Suppose you want to simulate an interesting molecule. In this case, like Femoku, right? Which is an interesting molecule that people try to understand, but it's kind of a little bit beyond the reach of our current methods classically. So this is related to like fertilizers. If people study fertilizers and how to make them better, they like to study Femoku, but it's kind of a big molecule, and it's pretty challenging to get kind of a description of this with a lot of approximations that we don't know if they are accurate or not. If you had a quantum computer with 200 qubits, we could simulate this, and there is some papers where people estimate this. In material science, for example, suppose you want to understand high temperature superconductors, right? And then for the experts, like suppose you want to simulate the Hubbard model, right? So that's what I mean by this, like more concretely. Then Hubbard model on an 8x8 lattice is already pretty challenging to simulate. So if you had around 70 qubits, you could already make some progress there and maybe do a computation of the Hubbard model that it's not possible to do today on our supercomputers. Once you go to 100 qubits or 1,000 of qubits, you can also try stuff in optimization. So all of these speedups, we think they are like exponential, right, with respect to the classical best methods. In optimization, they are more minor. They're like quadratic. Sometimes in a heuristic way, we think they can be larger, but what we can prove is quadratic. So you have to think about also the clock cycle of quantum computers. If it's very slow, they can be washed out. But eventually, we think they also be useful. And then if we're happy with like quadratic or polynomial speedup, there is many more applications, right? Like in scheduling, ranking, learning, and so on. And then if you do the estimates with perfect qubits, allow with like 100 qubits or more, you'll be able to get these speedups. So the situation seems pretty nice if you look in these terms, right? Because with very few qubits, you could already have all these kind of, in my opinion, striking applications, right? But of course, there is this big catch, perfect qubits, right? And they don't exist. Okay, so maybe let me just pass this because I'm going a bit slowly. So let's address this catch, right? So what happens is in the lab, right, is what I told you, right? We have like the qubits or the gates, right? Let's talk about gates is better. They are noisy, right? They're like 1% noise. 1 every 100 times, there is an error there. And then these algorithms, if you run with this kind of noise, they will just fail, right? They will not work at all. These errors accumulate, and in the end, you have like garbage in the end. So you have to find a way of getting more reliable gates. So we can try to improve these gates, but if you look, I didn't talk about the depth of the algorithms here, but if you think about them, for this one, for example, right, for RSA, but all of them, okay, so let's take actually for the easier one, which is here, like for Hubbard model. You need gates which are reliable at least 1 part in 1 million or 1 part in 10 millions. Okay, so right now it's 1 part in 100. We have to improve that to 1 part in a million at least. And for factoring, it's like 1 part in a billion. So it's a long way to go, right? This gap. And we can try just to solve this on the hardware, better and better gates, better material science. But it's a bit hard to see getting there, right? These quantum systems, they are very hard to isolate them and to control them and to operate on this level of finesse required. But there is another approach, and that's the approach of error correction. And this is quantum error correction, but error correction is used classically as well. So as I mentioned in our computers, we don't need error correction for computation. So transistor is so good, is like 10 in 13, right? So like one error in 10 to the 13 operations that we don't need it. But for example, in our hard drives, when we want storage, they are much more noisy, and we do use error correction. So what is the idea of error correction? Is that we want to protect information from errors using redundancy. So what's the easiest way to understand this? Is the repetition code. So this is still classical, no quantum mechanics here. So suppose you want to encode either 0 or 1, but there is a probability that the 0 becomes a 1 and the 1 becomes a 0. So if you just encode there naked, like 0, like this, if it goes to 1, there is nothing you can do, right? Your information is corrupted. But now suppose instead of on your hard drive encoding 0, 1, you encode 5 times 0 if you only encode a 0, and 5 times 1 if you only encode a 1. Then if there is an error, right, on like up to 2 bits, you can still correct, right? Because you can read, you can do majority voting. You see that there is like 3 zeros and 2 1. Then you say, oh, actually, this represents a 0. And the same thing here. So, now the probability, so if the probability of error was P before, now the probability of error scales as P to the power of 3, right? Because only if there is 3 errors, your logical information will be wrong. So that's the idea of error correction, right? That you can get some exponential suppression in the error rates that you have just by using redundancy, by increasing, the block size we call here. And here we are copying information, right? And one of the things we learn in quantum mechanics is that we cannot copy information. So it's unclear if you can do something like this in quantum mechanics, but it turns out that you can. They can be also error corrected quantum systems, and that's why we think we can, build a quantum computer eventually. But there is a price that you pay, right? So let me go back here. So there is an overhead, right? So here, instead of having to store just 1 bit, you have to store 5 bits, right? And more elaborate codes. And if you want to reduce even more the error rate, you have to use bigger code blocks. So there is a price, right? In overhead you have to pay. And I'll talk a little bit about, how this is done and how we're trying to improve this right now. But what we know today is that there is the error rates of your physical gates. No, they can go from like 10%, nothing can be done. Error correction will not work here, to like 0.1%, 10 to the minus 4, right? So here today we are, from here to 1% to here, 0.1%, right? The best results are around here. If you want to have many qubits, they are around here. So that's the curve, right? And then what we can do is say, okay, given these physical error rates that we have, and give us some targets, logical error rates that we want, for example, 1 in a million, right? How many qubits we need overhead for using quantum error correction? And we see that it's kind of, a little bit hard, right? So it goes from like 100 to 1,000 for the error rates that we have today. So this idea worked. Oh, sorry, is there?
Fernando?
Yes.
I have one question that is bugging me all the time with this
Sure.
idea of quantum computing. My problem is the collapse of the wave function.
Right.
So you have this very nice two-state system, which is essentially parameterized by an angle, if you want to actually a complex number alpha.
Yeah.
And everything is okay, but then you really get one or the other result with probabilities related to alpha mod squared and 1 minus alpha mod squared.
Yes.
So, and in other words, to get the reliable results, what do? You build many quantum computers and you arrange matters in order that this, you see what I'm saying?
Yeah, I see. Yeah, it's a good question.
This classical correction, I understand, but the question is the collapse.
Yes. So indeed, it's a great question, right? Because, if in your quantum computer you measure all your qubits, right, you collapse everything, there is no way to correct the error, right? So the idea of error correction, and then you learn too much as well. You corrupt your information, right? So you destroy your computation, right? So the idea of error correction, they have like many qubits now, but then you measure just some of them. You measure some of them, and then you try to infer errors on the other ones that you didn't measure. And then from this, zeros that you infer, you go there, apply a unitary operation, and correct the other ones. So you have to introduce some ancilla qubits, and you only measure these qubits, not the other ones. But by measuring them, and because they're correlated, you try to infer something about the other ones. I'll give you an example in the next slide.
So you will not make the others collapse, I understand.
Yeah, that's right. If everything collapses, you're doomed. So you have to be able to measure just some of them and not measure the others, and infer the errors in the others by measuring, a few of them. So, okay. okay, so I'll tell you exactly a little bit more how this error correction works, but let me now tell you, why it's so challenging to, get to this like useful regime of quantum computing as far as we know today. So suppose now our qubits have a realistic, or our gates should have a realistic error rate of like 0.1%, which is what we're converged to today, right? So today maybe it's a factor of like 5 times worse than that, like 0.5%. But we are getting close, and no one doubts that we'll get to 0.1% soon in many of these platforms that I mentioned before. But now if you look at the numbers, very hard, right? It's like 10 million qubits at least for breaking RSA, 1 million qubits for, or in the best case, 100,000 qubits to simulate these high-speed superconductors, and 1 million qubits for these like optimization applications. We are very far from that, right? So that's the the challenge ahead. Now going to the question, right? So let me tell you a little bit more about what is so far the state of the art for error correction, and then I will mention in passing just the research that we are doing, trying to improve on that, because I think it's important to do it, right? Because you see the numbers, they're pretty challenging. So this is called the surface code. It was introduced by Alexei Kitaev, who's a professor here at Caltech as well, and that's you can think it's some version of repetition code if you want but for quantum information now, and then it gets more complicated. So what happens is that imagine that you have a square lattice of qubits. Okay, whenever you have like a dot is a qubit, and you want to encode 1 qubit here. But then you distribute these qubits in a non-local way to protect them, and then what you do is the white circles, they are what we call ancilla qubits. So these qubits, we keep measuring them, apply gates and measure them, apply gates and measure them, and then we get what we call syndrome information. We get some information about what are the possible errors that is happening there. And the black circles, they are what we call the data qubits. These we don't measure. This is where the actual computation is and where the actual qubit is. And then we apply just these simple circuits, right? Whenever we have this kind of like cross, this green cross, what we are doing is a simple circuit. We are basically, we have one data qubits. We apply a bunch of C0, right? Sorry, this is where I'm doing. Wait, did I do something wrong? Yeah, I apologize. I did something wrong. So the data qubits are the white ones, and the ancilla qubits are the black ones. Sorry. And then what you do, you basically copy information from the data qubits for four nearby data qubits into one ancilla qubit, into one ancilla qubits, and then you measure this ancilla, right? Exactly, you collapse it. But then if you collapse it, you only learn about the parity of these 4 nearby qubits. You do not learn anything else. You just kind of measure the z operator, right? Or parity of the z operator. And the same thing with this other, we call plaquette, XXXX operator. So if you do like that, you see that you can detect errors and you can correct them on the qubits you don't measure, unless there is a sequence of z errors which goes around the square. Like it's like z on the x or the y direction, or the same thing for x. So you see that. So this gives a lot of suppression. So the probability of logical error rates, right, on the left, scales like this function. That's, don't worry too much about this, but there's the physical probability of error. There is a prefactor, 100, large, but then d, which is the distance of the code, right? If the physical error rate is more than 1%, right, that's the threshold, what we call. Then if you build larger and larger systems, larger d, the logical probability of error drops exponentially. So this is like distance, right? 5, 9, 15 that I put here. These are physical error rates, 0.5%, where we are today, kind of, 0.1%, where we'll be soon, I think. And then you see that the probability starts dropping a lot, right? So 0.1%, it can be 10 to the minus 9, but you need distance 15, which in the number of qubits, if you count, is like 2 times distance square roughly, is like 435. So it gets challenged. Yes.
Just another question, which is maybe naive, but
yes.
If you make one qubit collapse and the qubit is coupled to the other qubit that you don't want to perturb, in some sense you disturb also that one. If they are not coupled, you can let it collapse and
Correct.
the other one doesn't care. And on the other hand, you need them to be coupled because otherwise it doesn't carry information. So there is some sort of limited, some sort of competition between two effects, not perturbing it and being correlated to it.
That's exactly right. Yes, indeed. There is a back action, right, from the measurement that you make here to the other qubits. But then you have to design your error correction code in a way that this back action, is not disturbing the information, but it's kind of it still allows you to detect errors in these other qubits, right? So, so indeed, it's like two competing effects you have to handle, right? So you have to learn something about the qubits, but you cannot collapse this qubit, right? So, but that's why you engineer this in a way that the only information that you learn about these data qubits is basically the parity of this observable, right? And then the quantum information is encoded in a subspace which is not affected by this. So it's like So anyway, so if you want to get to this target application, is what I mentioned, right? So for factoring, you need 6,000 logical qubits and 10 to the minus 12 error rates. Then this means you need like 10 or 20 millions, right? 10 to the minus 3 error rates. For Hubbard model, we need around like 132 logical qubits. Maybe it shouldn't be 70. There should be 132 because you need it's a fermionic system, so you have to double. This means on practice you need like 300,000 qubits, at 10 to the minus 3 error rate. So very challenging, right? But then, maybe I'm going a bit slow, but let me mention this quickly. This is the approach, for example, that Google is trying to do, right? Just surface code, try to scale up, or IBM as well. But it's using transmons, right? Using the superconducting qubits. But it's pretty hard to get to the end goal, right? So the question is there like hardware efficient fault tolerance, right? So this is called error correction fault tolerance, right? We want to make a quantum computer which is fault tolerant to errors, right, in the qubits. So is there a more efficient way of doing that? So, this is like, you should try maybe to correct as much as possible in the hardware level, right, not in the software level, as like this error correction codes is kind of doing. And people try that, right? So like Majorana qubits, many people try, including Microsoft, right, and many people in academia. So the idea there is that if you can create these Majorana fermions, they might be pretty good qubits because they have some topological protections. They haven't been realized yet, so it's hard to tell what will be the gain, but it's promising. People consider like 0 pi qubits, special kinds of superconducting qubits, and we can encode in harmonic oscillators like cat qubits, which is the approach that we are doing. And potentially this can give some we are doing, but also people do it at Yale a lot, and Paris, and many other places. And I think it's worthwhile thinking about these approaches, but there's a risk, right? So if you put excessive focus on building block like a qubit, namely, you might lose sight of the final goal, right? So what is the final goal? We want to have a logical qubit with target error rates for useful applications, right? And then many times, people can try to optimize, the coherence time or the physical error rates, or the probabilities of winning a Nobel Prize because it's beautiful physics, and so on. But this might not be necessarily the right metrics, right, for building a quantum computer. So this is good to have in mind. So what we're trying to do at Amazon is be pragmatic, right? So we're trying to take like an agnostic approach and really be open to hybrid of hardware and software error correction. It's very early on. Probably we don't know the best way, but we can try, right, to see what is out there and come up with a plan for that. So, but we have to be able to evaluate, candidate ideas quickly, and we shouldn't get attached, right? So what we're trying to do, and what we did in this paper that I'll just mention one slide because of time next, is to work backwards from the end goal, like from a target application. In our case, we chose, solve the Hubbard model on 8x8 lattice, right? Then think about what is the full stack for the proposed architecture, right? How we get there from the application, the error correction architecture, all the way on the hardware details, right, of the experiment. And then I think if you think about that, we can avoid some of these pitfalls that I mentioned, right? So maybe you have good coherence of the qubits, but only pretty bad physical gates, right? That might not be good. Or maybe you have bad physical gates, but once you think about the error correction, it leads to actually good logical gates because error correction is so efficient. And we kind of see that in the approach. Or maybe the logical gate set that we can get has a very high overhead for the algorithm you want to run. And so it's not so good, right? Or maybe the gates are just very slow. And that's also bad because it's all about, speed matters here, right? So for example, ions are extremely slow. Superconducting qubits are faster, but maybe not fast enough, right? So we have all these, metrics to think about. So maybe, I won't have to talk more about this, but let me finish with this last slide. We put recently a paper out, like it's the first paper from from the quantum team at Amazon, where we thought carefully, and there's a lot of people in this paper and you know, like theories, right, in my team, but also the experimental team that we are working with, which is led by Oscar Painter, who's a colleague of mine here at Caltech, and also like other people in his team. And what we try to do is to think about how we can build a quantum computer, right? But thinking about as much detail as we could. Of course, it's hard to think about all of them, right? But using these cat codes that I mentioned, which is the states of light or even of vibrations. You can use phononics for that as well, that I didn't tell you about, but that is this more hardware efficient way of doing quantum computation. And really think about, you know, how we do the error correction, right? Not using surface code, but using something else, using what we call like a repetition cat code. So it's a new way of doing error correction. And then working out what we expect to be realistic parameters that we can achieve in the near term, right? And then thinking all the way to the overheads, right? What it takes to do it. And then what we found is, I think it's like promising, but you know, there's more work required. Suppose you just want to have like 100 logical qubits and 10,000 logical gates. Okay, so this is enough to go to a regime where we cannot simulate this classically anymore, and right, and potentially there is some applications, but we don't know if there is applications yet. Right, for application we need much more gates. But then we found that actually with like from 1,000 to 2,000 like physical qubits, and this means, you know, these novel qubits that we propose, more hardware efficient, we can do that. So that's kind of an intermediate goal, right? So putting 1,000, 2,000 qubits, superconducting qubits, it's hard, but it's something that we think, you know, we might be able to do in the next 5 years. And then we identify a possible regime for fault tolerance that we think we can get there, like as a first step. I think it's pretty exciting. But if we want to get to this regime of actually applications of a problem that we don't know how to solve today, for the Hubbard model, right, which is one example, we find 2,000 physical qubits will be enough. And before, if I mention you, right, surface code gives like you know, almost 200,000. So there is like a 10x improvement. So it's still very challenging, but we are seeing a lot of potential in this kind of cat codes and this more hardware efficient way of doing fault tolerance. And this is what, you know, our research will be doing in the next few years. So let me mention, let me conclude. So right, so we are doing this at the AWS Center for Quantum Computing. So there is a building. It's almost done here at Caltech, but it's this, you know, vision from AWS that quantum computing is worthwhile, but it's a very long-term activity. So we have theory team, which is led by me, and the experimental team led by Oscar. And we are doing research, right, on trying to build a quantum computer. That's our long-term goal. We're also hiring. So, you know, if you're interested, please feel free to reach out to me. And or if you have people, talented people that you think might be a good fit, I'll be happy to talk to you. So quantum computing, right, it's a marathon, not a sprint, right? So I think it's very important to take this holistic view of like hardware, error correction, algorithmic primitives, and end application when you're thinking about future use cases of quantum computing. And I didn't talk much about it, but I think these cat codes are pretty promising, but there's way more work needed. There's analogs to them like GKP and Kirkat. There's experiments that we are doing, and we hope to get some more clarity on this soon. And that's all. Thanks a lot for tuning in. So I'm happy to answer any questions you might have.
Okay, thank you very much, Fernando. It was a great talk. Okay, let's see if there are some questions from the audience. Otherwise, I do have a question for you. Okay, so Marco, please.
Hi. You touched upon scalability, and I was wondering whether you can comment a little deeper on that. I mean, what's the most promising? I thought it was superconducting qubits, but I may be wrong. So I just want to understand better about scalability. Thank you.
Yeah. Okay. So it's a great question, but it's I think the fair answer is that people are making different bets for different reasons, and you know, it's not clear what is the best way to scalability. I share your opinion that in my opinion, and the other people work with me, superconducting qubits seems, you know, the right bet right now, and that's because it's solid state. It helps, right? I think there is a very clear path to 1,000 qubits on a chip, right, or a few thousand qubits. More than that, then is a question of cryogenics, right? So you build a really, really big fridge that it's hard, or you have to build many fridges and then you have to connect them which it's possible, but it's challenging, right? So by superconducting qubits, there is a clear path to 1,000, I think, or a few thousands. More than that, I think it's still promising. But there's then other approaches like ion traps. Then I don't think they can go more than 40 qubits in one trap. They're more because then they just get too cramped there. Then more than that, you need this kind of optical interconnects, right? You have to build different traps and connect them by photons, right? So you transfer the information from the ion to a photon. You make the photons interfere and then you connect them. But it's pretty challenging experimentally, I would say. But people are trying, and hopefully they can work it out. Photonics, on one hand, is good to scale up because the foundries can build for you, but it's very, very challenging to make, right? The good enough entangled sources that you need. So I would say they all have challenges for scalability and kind of different challenges, right? So it's good that there is this kind of diverse investment right now because let's see who will make it, right? But yeah, so let me stop at this. But there's a lot to say about scaling up and what are the pros and cons of each of these alternatives, right?
Thank you.
Great. So Stefano Chessa, please.
Hi. Yeah, I would like you to comment about the claim by IonQ and recently also by PsiQuantum about their roadmaps. And in particular, what happens if the promises are not kept? I think you're familiar
right.
with the, okay.
Yeah. I mean, if I put my Amazon hat, right, the policy of the company is not to comment other people's roadmaps, right? So, we are wishing them the best, right? So if they can meet this roadmap, it will be fantastic. Like it will be a big win for all of us. If I put my scientist hat, then I don't think it's very credible, right? The roadmap they're putting forward. So, I don't think no one is going to get like useful application in 2-3 years. It's just not possible. I don't see a path for that, right? It's very challenging, as I just explained to you. Even 5 years would be a huge breakthrough, right? Which, from what we know right now, doesn't seem possible, in my opinion. So I do think, right, that in general, right, it's not about them, but in general, it's very important to keep real about the state of development, right, and to keep real about the timescales, right, to be realistic about it. It's a long road ahead of us, right? It's worthwhile doing that, right? And I think many people realize that, right, in industry and in science. But I think it's very important to keep expectations realistic, right? Which not always is happening right now.
Okay, thank you.
Okay, Augusto, I see that you have.
I have one last question. From the impression that I got from the presentation that you gave us, which was very nice, by the way, is that what you're doing at the moment is more reminiscent of what commonly is a microprocessor with a definite purpose to begin with than a computer that you can program and use for different purposes. Is it correct? In other words, you build the quantum computer with the clear idea in mind of what you want to do with it, like solving the Hubbard model. With the standard classical computer, so to speak, you change your program and you do various things. With a microprocessor, on the other hand, which is another device which is commonly used, you only do one thing and it does it very efficiently. It seems to me that you are more aiming at the second type of situation for the moment.
That's a great question, and indeed, right? Some people say, "Oh, let's do like quantum computer, really think about application, and then maybe even you don't need error correction for that, right?" So once you do error correction, as we are doing, actually, it would be a general purpose quantum computer. You can run any circuit that you want. So in that sense, it's not the case that we're building exactly just to solve the Hubbard model. I only use the Hubbard model because that's the application that we can run, which has the fewest number of gates, as far as we know, right, from the other ones that I mentioned. So this will be the first one.
Error correction would grant the possibility of general programming. Okay, I understand.
That's right, but like the numbers that I gave would only grant this the possibility of general programming when you on algorithms that you can apply at most like 1 billion gates, right, or something like this.
This might
not be enough for factoring, right? But you can run any circuit indeed on 1 billion gates.
There's a big redundancy problem and all the like. Okay, thank you very much.
Yeah, exactly.
Okay, great. So if there are no other questions, I can maybe ask you a couple of questions myself. So, I see that Marco has another question. So please, Marco, go ahead.
Thank you. So I was going. I wanted to go back to the issue of silicon photonics, which I find interesting. But photons, don't interact in vacuum. So similar to the superconducting circuit, whether you need a nonlinear element, you can put a piece of nonlinear material and make photons interact. You take a material with strong, second order nonlinearities, and you make photons interact. Does anybody, following this path of implementing highly interacting photonic systems, as far as you know?
I mean, I don't know so much about this area, so I could be wrong. I think there is some people like academic experimental groups that they think about that right, nonlinear optics, and they try to. There is a bunch of proposals where people exactly propose that, right, to use nonlinear optics to implement the gates. But the approach that I think people are trying to scale up, for example, at Sci-Quantum, right, and is more, you basically introduce the interaction by making measurements, right? So if you make measurements, it's also nonlinear, right? So you have like okay, you do have an initial entangled source, right? It can be like parametric dial conversion, the simplest way, right? So you do generate entanglement there. But then if you also make measurements, you can create this initial like resource states, and then after that is just linear optics that you need, right? So kind of they push all the nonlinearities to the preparation step, right? But you could think about doing the gates along the way with nonlinear optics, but I don't think anyone is trying to scale up this approach right now, as far as I know.
Okay, thank you.
Great. Any other question, comments? Okay, if not, so I have two questions. One is a technical one. So I really would like to know what exactly a cat code is. So yeah.
Sure. Let me tell you. Thank you for the question. But are you seeing? Oh, maybe I have to share my screen again, right? So, or you see my screen?
No, we are. I mean, I see the slides. I think that also the others are.
Okay. Okay. Perfect. So, can you see it now? This slide, two-component cat codes.
Yeah, maybe if you go widescreen.
Sure. Yeah. Okay. Widescreen. Okay, fine. Yeah. So Vittorio, it's very simple. It's there's some errors. But you understand very because you work a lot on simple things.
Sorry,
right?
sorry. There is some feedback in the so we hear some noise. I don't know what.
Maybe someone has to. How about now?
Oh yeah, now
it's better, right? Yeah, Vitor, it's like similar to stuff they worked before. So we encode the 0. Okay, we have a harmonic oscillator. Okay, and then we use coherent states. So alpha is a coherent state of amplitude alpha, mean photon number alpha square. So we encode 0 into alpha and 1 into minus alpha. They're not really orthogonal, but they're almost orthogonal, right? So actually the complementary basis is orthogonal, and that's the one. But you can think simply approximately like this. So you have these two harmonic oscillators, and mean photon number, think about something like 8 or 10 or 6. So they have, they're pretty orthogonal, these two states, right? And this is where encoding information. But the approach that we're doing, using coupling to a nonlinear element, like some kind of transmon, what you can do is engineer a BEF. So you engineer a BEF on this harmonic oscillator where you lose photons by pairs, okay? And you put a 2-photon drive as well. So then you have this master equation. This is like the jump operator that you engineer with strength kappa 2, which is a square, the annihilation operator square minus alpha square. So you see that this dissipator will stabilize the ground state manifold, right, or the dark state manifold is alpha minus alpha. So and then what you can calculate is that there is a big energy penalty for going from alpha to minus alpha. So you exponentially suppress in alpha bit flips, X errors. But you still, of course, have decoherence, right? You have kappa 1 photon loss, kappa phi dephasing, and then this leads mostly to Z errors. And then you have to correct the Z errors on the outer codes. But the cat code is just using two coherent states to encode your information, basically.
I see. Okay. Thank you. I do have a final question if there are no other comments from the audience, and it's a very practical one. So you are the head of the quantum algorithm department of WS. No? Can you tell us a little bit more about this structure? What exactly is this this enterprise?
Sure.
So how does it work? So you get money from Amazon?
Well, it's Amazon has been thinking about quantum computing for a while, right? But then there was a announcement in the end of 2019 of a few of the activities that the company decided to do. One is this cloud service called Brackets, right, which gives access to quantum hardware that we have today, right, from different companies to people interested in accessing them, right? So it's, on a scientific level, it's pretty interesting, right, because it's basically you have a physics experiment, right, on your computer, right, that you can check, and it's a great way to see progress in this hardware along the way when it moves on, right? But as part of that, another direction that the company decided to do is that, what is the challenge right now? Of course, is to give visibility to the state of the art, but also to figure out the technology, right? So they decided, to have an internal R&D efforts on scaling up this quantum, technologies, right, and quantum computing in particular. So this AWS Center for Quantum Computing that I mentioned, right, which is ran by Oscar Painter and myself, it's the R&D side of this, right? So really what we're trying to do, so we are part of Amazon, right? And we have, a bunch of other Amazon employees working with us, scientists from Amazon working with us on quantum computing. We also partner with people in academia, like Caltech, for example, but also, we have people in Stanford, Harvard, and so on. And the goal is this, right? So get, a bunch of people and try to figure out all these technical challenges and hopefully one day build a quantum computer.
Okay, I see. Very interesting. Okay, so if there are no other questions, comments, I think we can thanks Fernando for his nice presentation. It was very interesting and we learned a lot from it. Okay. I think
thanks a lot, Vittorio, for the invitation. It's a pleasure to see you.
Unfortunately, I cannot see you, so basically I'm talking and I just see slides, but that's the problem. Okay, so thank you very much. Now I see you.
Oh, okay.
Bye.
Right.
Bye-bye.
Great. Bye-bye. Thank you.
Bye. Bye, Augusto. Thank you. See you.